Hi, everyone. Really glad to be here today to present about my open source project, OpenEvolve, and some of the work that we've been doing around building open evolutionary agents. So I would like to start from the very beginning and talk just a little bit about the genesis of this project. We started off earlier this year, right after this paper that was published from Google DeepMind, AlphaEvolve. And when I read this paper, I was intrigued by two things. One was that this was one of the very first papers where somebody had claimed that LLMs can be used to do a novel discovery that surpass state-of-the-art solutions on scientific and algorithmic problems. And second was that on the surface, it looked like the approach is very simple. It just adds a evolutionary framework on top of LLMs and represents existing genetic operators that we use in evolutionary algorithms using LLMs. So with that in mind, I actually decided to do a replication of the system because AlphaEvolve was not available and still not available till date. And we decided to build a similar system and release it to open source. So that was kind of the genesis behind creating OpenEvolve. We wanted to stick to, in terms of the architecture, similar to the spirit of what was described by DeepMind in their paper. So the architecture of OpenEvolve is very simple. It has four kind of distinct components. Each one of them is asynchronized. So on one hand, we have the LLM ensemble, which is used to generate code modifications. It can be a single LLM, it can be multiple LLMs. We just interact with the API. So you could do the inference at any place, and then you could just use it in OpenEvolve. Similarly, we also have an evaluator pool. So by default, we do parallel evaluations. So depending on the programs that we have, you can expand the pool and you can increase the speed of evaluation. The evaluators will just test the programs and assign some metrics or scores. These are the scores which are used as a fitness function for the evolutionary loop. On the other hand, we have a program database. So we maintain a database of evolved programs or intermediate programs, and each program we store the set of metrics associated with it. And then we have a prompt sampler which samples from this program database, and then depending on the iterations, it would go ahead and ask the LLM to update the programs, right? So all of this is orchestrated by using a single controller which controls this evolutionary loop. So this is actually very close to what has been described in the AlphaEvolve paper, at least in terms of the architecture. So once we have this, just to give you a sort of an understanding of how you can take a particular program and run it through this whole evolutionary cycle, I'll just take a simple example of the maximum subarray sum problem, which is a well-known problem where you're given an array of integers and you want to find the contiguous subarray with the largest sum. So in this particular example, you can see that the array from index 2 to 5 has the sum 6, which is the maximum for this particular array, right? So how do you actually go about solving this efficiently, right? So now this problem obviously has a known solution, but it's a good example just to give you a taste of how one could go about evolving such a solution. So if you want to start off, you can actually implement a very simple or rather naive solution to the problem where you just recursively enumerate all possible subarrays. So you start from the first index in the array, you go down till the last, and then for every index you create subarrays of size 1, 2, 3, all the way till n, and then take their sum and see which one is the maximum, right? So now if you look at the time complexity of this naive solution, it's going to be order n cube, right? Which is very slow. It takes 3 nested loops. So we could start with some solution like this, and that could be your initial code that either you have written or it's been generated by some other LLM, right? And after this, what you need for OpenEvolve is just 3 things. So one is the initial code. Second is you need to have an evaluator, which will be used to compute some score, which will be guiding the evolutionary process. So in this particular case, the score could be either related to correctness or to speed. So we need both because we're trying to optimize the problem. So we might return a combined score which takes into account how correct it is and how fast it is when evaluated. And finally, we just need a configuration which tells OpenEvolve what models to use and some of the configurations for the internal evolutionary process, specifically how many islands that the evolutionary process has to control and so on. So with just these 3 inputs, you can just start OpenEvolve, and evolution will guide the process and find the best possible program, right? So we have implemented what is known as an island-based evolutionary process, where each individual island maintains the population, which is diverse and separated from each other. So each island has its own evolutionary loop. So in this particular example, you see that there are 5 different populations, and each individual in the population is a particular program, which is a solution to the problem, right? Every n iterations or every n generations, we do migrations where we take the best performing programs from one island and we move them to another. So this particular path, it's not something new. It is a standard island-based evolutionary algorithm. And we've chosen this because having all of it in a single large population was very slow for convergence. And also it doesn't help maintain diversity. So this way you can actually maintain diversity throughout, while the best solutions still have a chance to spread through the migration process. So within a particular island, you have individuals, as you see here, 5 programs. Each of them have some different scores, which are found from the evaluator. And the iteration, each island runs on its own evolutionary loop. And we run all islands evolutionary loops in parallel. So I mentioned in the evaluator pool, we actually allow all workers to work in parallel, and we attach each worker to a single island. So within the island, we go through the full 4-step process. You select the best program from the island. You use an LLM to do mutation, which is like a standard EA operation. And then you create a new program, which is then evaluated and then replaces the worst program. And these iterations are continuously repeated. Within the part where we use the LLM to do the improvements, we have a very simple system message or a system prompt. So it's the same prompt that is sent to all the evolutionary loops. So it's not different. So there's a single prompt that you put in the config, and then that guides all of the programs throughout the process. So at each step, you will select the best performing program from the pool of the islands that you have. You will use a LLM with a prompt which says something like, improve the solution, fix any bugs, optimize, so and so. These are the metrics which were there for the best solutions, etc. And then you'll ask the LLM to generate a new version of the program, and then you'll evaluate the new version as well. And then if it is better, you'll replace the worst program in that island, and so on and so forth, right? So just the standard EA process, and it continues in a loop. And in this particular case, after a certain number of iterations, you'll notice that OpenEvolve is actually able to find a well-known existing algorithm which can solve the problem in order n time and takes only order one space just using 2 variables, right? So this is just to walk you through very quickly of how the process works. But obviously, you don't want to apply it to such simple problems for 2 reasons. One, because an LLM probably has already seen this as part of its pre-training set. And also, you don't need to set up all of this to discover the solution. There are probably, if you prompt the LLM directly, it might be able to tell you this. But where it really works well is problems where you don't know the solution or you're actually trying to improve the state of the art, which was one of the focuses of the AlphaEvolve paper. In order to do that, we set out to replicate some of the problems that were described in the paper. And one of the first ones we did was the circle packing problem. So it involves placing n non-overlapping circles inside a unit square to optimize a specific metric. Now, in this case, the metric is the sum of the radii of all the circles, right? So for n is equal to 26, before AlphaEvolve, the best known solution for this was something that would optimize it to 2.634. And in AlphaEvolve, they were able to find a better solution that improved on the state of the art. So our initial goal was to see if we could match or exceed this result, which we were able to do with OpenEvolve. And just to give you a sense of how the initial program can be, it doesn't have to be something very optimized. It can be just something totally random. Or in our case, when we started with this, we just placed all the 26 circles in a very simple structure in the square. So we just put 8 in a ring, and then we put 1 in the middle, and then we just put all the other 16 all at the corners around, right? And then we started the evolutionary process. And by the time you reach around 10, 20 generations, you'll notice that the system has already discovered this hexagonal arrangement, which is something that you would do yourself if you were trying to do it by hand, or if you were trying to set up these things. You'll realize that instead of going across, if you put it in this kind of 6 circles in hexagonal arrangement, that actually helps, right? Then by around 100, 200 generations, things start to get a lot more interesting. And you'll see that the arrangements that come out from OpenEvolve, where it's really trying to fit in a circle and it's trying to make the circles as large as possible, right? One thing you'll notice that in this particular case, the output is not really another algorithm, but it's like literally the placement of the circles, right? So because that's why we started with. But if you run it for enough number of iterations, there will be a kind of a phase change or emergence where the system discovers using algorithms or simple programs to do these arrangements rather than put them directly. And when we went through this around 400 or 500 iterations, the system was able to discover a particular algorithm which uses SciPy optimize, sets up the constraints, and then builds up and solves these constraints to discover and set up the arrangements. And finally, it came up with a packing arrangement that looks something like this, right? And this particular arrangement, so when we compare, so AlphaEvolve did not release the code of the system, but they released the code to verify the solutions they built. And this particular solution on the right you see is from the AlphaEvolve's notebook, and this the one on the left is what was discovered using OpenEvolve. And you can see that these are essentially exactly the same packaging which was discovered, right? Subsequently, others have improved upon this for this particular problem, and I think right now We've gone even beyond 2.635 or what was reported in the AlphaEvolve paper. So we've gone even beyond that by using some modifications. So this just gave us good assurance when we were building the system that okay, this is something real and it can be used to improve, and it's able to replicate some of the work that was there in the paper. The next thing we wanted to check was something which is also in the paper, but around using Gemini to improve the attention kernels for TPUs. In our case, we wanted to try if we could do something similar for Apple's MLX metal kernels, and we chose a very specific transformer for doing it, which has a group query attention. Now, this is a very hard problem because MLX has its own implementation of the scale dot product attention, which is written in highly optimized C++. And these kernels are actually very optimized. So it's extremely hard to outperform them by using something else. And even on a smaller subset of problems or a smaller subset of workloads, right? So we managed to do that for this particular group query attention. And we noticed very similar thing like we did with the unit circle packing example. There are certain generations after which you see some phase changes or suddenly something starts working, right? So this particular evolution went through 25 different generations of kernel optimizations, and it discovered three different optimizations. The first one was this SIMD. Second was a known two-pass softmax algorithm, so instead of a single pass, and then finally there was some memory optimization, right? So and at each point there is like improvement in terms of the fitness score, and then the population diversity keeps going down, right? We had a very strong or very large benchmark suit. That's why we do not do too many generations. So this is kind of how the performance of the evolved kernel looked like on our benchmark. And overall, there is some categories where there were some degradations. For example, in code generation and in short context, the decode speed actually goes down. But what we noticed is that on an average, using this OpenEvolve, we were able to evolve a kernel that was on an average 12.5% faster than Apple's own scale dot product implementation, right? And for some of the cases, almost twice as fast in some of the examples in the general task category, right? So this the reason why we cannot do so many iterations, or the reason it took so long, is that each of this benchmark is actually a large number of test cases. So whenever we do the evaluation, we have to run the benchmark on the exact hardware which we are trying to optimize, and in this case, an Apple M3 or M4 machine. And each iteration would run a few hundred of these test cases to gain assurance in that what we're discovering is actually real optimization. So a large amount of what needs to be done with the OpenEvolve is to write these really nice evaluators, which are rigorous and efficient. We also report some results on this relatively new benchmark called AlgoTune, which was published recently. So this is a benchmark of 154 tasks for general purpose numerical programs. And in the paper, they also report a agent called AlgoTuner, which is able to improve on these. Now, this is also an extremely hard benchmark. For most of the tasks, if you go and see the paper, you'll notice the actual task is just the standard library. Like they just do a fast Fourier transform dot convolution, or so it's really the standard API implementation from a standard library, either from NumPy or JAX or something, and it's extremely hard to optimize on top of it because those are well optimized programs, right? So on this particular benchmark, so the results on the bottom are from AlgoTuner, which is the agent they built, and they got the best result using O4 Mini, and they were able to improve upon the speedup was around 1.72 overall across all the tasks. When we used OpenEvolve on the same benchmark, we were able to actually push that number to over 2x by using even a relatively less complex model like Gemini Flash. We also tried a number of open models, which are of a decent size that can be run locally, for example, Gemma 3 or Qwen 332B. And we saw that we are able to use those models as well to improve on average up to 1.6 to 1.3x over the benchmark. Right. So this gives us some sense of the fact that you can actually spend a lot more time compute at inference and improve the performance on a benchmark while using a model which is maybe not as complex or big as some of the frontier models, right? So with this, and so far our experience of using OpenEvolve or a number of other things, I think there are some learnings that we have learned in terms of how to approach this problem for evolutionary search. So one of the first things is that we have to choose the right abstraction at which we want to do the evolutionary search. So the very first example I shared around circle packing, we started with a program which is literally just putting the circles on the unit square. So we started with a program which directly prints the arrangement rather than a piece of code. And that is okay. Eventually, the system was able to discover a program, but you could have started at a much simpler a random program which just places circles randomly, and that maybe it would have helped in increasing the convergence, right? So it's always tricky to figure out at what abstraction we want to do this, because you could do the same thing at multiple abstractions. Second, which is more of a practical issue, is that whatever code you write, you have to be very careful and strategic in allowing or disallowing certain existing libraries or APIs. So, for example, in AlgoTune, many of the discovered optimizations actually use JAX or use a just another library which is not mentioned. And if you do not allow that as part of the evaluator, it would not work. So you have to actually really decide and figure out what existing libraries, SDKs you want to allow, or what you want to disable. The reason you might to disable something at times might be if you're trying to discover something new and you don't want to use an existing implementation. Third is the prompting in this particular case looks very different from usual prompting, either when you're doing a large multi-turn conversation with a LLM or in a chatbot, or you're doing like a large long horizon agent loop where you have multiple tool calls. The trajectories that come out of these evolutionary search are very different. And so our system prompts or the system message we write actually contain a lot of information which may not come up in every single iteration of the program. So you have details around if this happens, do this, or try to use this library, or if you're on this hardware, do something else. So all of these are written in such a way because we are trying to guide not just one program, but an entire population of programs using a single prompt. Uh, I already mentioned this, but writing the evaluators is very, very important. So we do have support for what we call cascading evaluations, because at times what you want to evaluate the program on might itself be a large or complex benchmark, like in terms of kernel evolution. And you may not want to run all of it at all times because it'll just be too expensive. So you have a system of cascading evaluations where you can set up a stage 1, stage 2, stage 3, and you can only run the evaluators if they clear the earlier stages. And writing the evaluator or building the evaluator is really where we spend a lot more of our time, because that really guides the and performs the evolutionary pressure on the algorithm to discover something new. And finally, it still requires a huge amount of human ingenuity in formulating the problem. So just taking an initial version may not always help. So it requires several iterations through the system to actually formulate the problem and examples, which I just showed you. Now, that said, I do think that this evolutionary coding agents actually present a new kind of paradigm, specifically when you think about inference time scaling. It represents like a different axis in terms of where you can spend some compute at inference time, which is distinct from either sequential or parallel test time computing. So this just provides us another way for us to improve the performance of a model at runtime without doing any training. And it's the trajectories, like I mentioned earlier as well, that come out of these evolutionary runs are very different from what you would get either by thinking longer or generating more tokens or actually doing large parallel rollouts, right? Uh, Second, uh, it provides a very good way to do search with LLMs in this evolutionary framework. So last year, a lot of people tried doing stuff around MCTS or Monte Carlo tree search or A star search and so on, and try to combine that with LLMs with varying degrees of success. But I think that this evolutionary approach, you do get a nice way to actually drive search with LLMs, where the evolutionary framework is providing the overall uh, guardrails for what the LLM is supposed to do or not. And that gives a nice way to combine genetic algorithms with LLMs. Now, I think the last point here is more about what is next in terms of what else we could do. And one of the things that we are looking at is also some of the evolutionary agent trajectories. Is there a way to actually do, say, RL on them or do reinforcement learning using the rewards that come out of OpenEvolve? And there is a patch that somebody recently submitted to OpenEvolve, which allows you to generate these RL-like trajectories. And the question is, if you distill these evolutionary agents into the base version of the next model, or if you do RL, can you actually convert some of this compute that we are spending at inference time at training and then get better performance out of the models directly? Um, that's all my time. So I'm happy to take any questions. Here is a list of links if you are interested to know more about OpenEvolve and some of the resources to help you with that. Thank you.